तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So let us start today with problem set 5, which is on Pauli matrices and spin half and so on and so forth. I mentioned already that the smallest non-zero quantum number for the angular momentum is a half, and spin half or j equal to half, s equal to half, implies 2s plus 1 equal to 2. So everything is in terms of 2 by 2 matrices. And physically, the first example that we have of 2-dimensional linear vector space is the spin of the electron, the spin states of the electron, which are described by the two ket vectors, as I pointed out up. This corresponds to s equal to half, sz equal to half, all in units of h cross. So I should write this. In our Jm notation, and similarly spin down is what I would call half minus half. So recall our notation was J and M, where this is always the quantum number associated with s squared. This has always got eigenvalue h cross squared, j times j plus 1, j squared rather, and jz has eigenvalue h cross m. So these were two mutually commuting observables, and my angular momentum states are categorized, are labeled by labeling the total quantum number, angular momentum quantum number, and the projection quantum number m. For the spin half particle, like an electron, this number is always a half, so I do not really have to write this, I just have to write what sz does. This corresponds to eigenvalue plus half h cross minus half h cross, and pictorially one would like to say that this corresponds to a spin up or a spin down, so I use this kind of notation for it. Now we already know that the spin operator of the electron can be written as h cross over 2 times the 3 Pauli matrices sigma, and these matrices have the standard representation sigma 1 equal to 0 1 1 0, sigma 2 0 minus I 0, sigma 3 is 1 0 0 minus 1. That is a very useful representation for spin half, because each of these sigma matrices, the square is equal to the identity matrix, so sigma I squared equal to the identity matrix, and they obey interesting commutation relations. In fact, sigma I sigma j equal to I epsilon ijk sigma k. So sigma 1 sigma 2 is equal to I times sigma 3 and so on. It is easy to see that the commutator sigma I sigma j of course is equal to 2I epsilon ijk sigma k, and the anti-commutator sigma I sigma j plus is equal to, what is this equal to? the square of each of them is equal to 1, and if I is equal to j, then you just get the unit matrix, twice the unit matrix. So what is this equal to? This stands for sigma I sigma j plus sigma j sigma I, the anti-commutator. What is this equal to? It is 0 if I not equal to j, and if I is equal to j, then it is equal to 2. So what should it be? 2I delta j ij, twice the unit matrix times delta ij, the Kronecker delta. What are the eigenvalues of the sigmas? 1 and minus 1. What about sigma 1 and sigma 2? What are their eigenvalues? Also 1 and minus 1. They all have the same eigenvalues, 1 and minus 1. The square of each of them is equal to the identity matrix. They are linearly independent of each other. The 3 sigmas are linearly independent. No sigma can be written as a linear combination of the other two, and you could take any arbitrary matrix M, any arbitrary matrix A, any 2 by 2 matrix A can be uniquely written as a combination of the sigmas and the unit matrix. So you can always write this as A naught times the unit matrix plus AI sigma I summation I equal to 1 to 3. This is unique. Any 2 by 2 matrix can be expanded in this form. What is A0 equal to? What property of A does A0 reflect? The trace. What about the trace of the sigma matrices? What are the traces? 0. So it is clear if you take trace on either side, the trace of A is twice A0. So A0 equal to half trace A. Okay. What about AI? If I formally want to invert this and write it, what should I write? What about AI? Suppose you want to find A1, what would you do? I would multiply both sides by sigma 1, and then it becomes sigma 1 A on this side equal to A naught sigma 1 on this side plus A1 times the unit matrix, right, because sigma 1 squared is 1, plus A2 times sigma 1 sigma 2 plus A3 times sigma 1 sigma 3, and then what? Take trace. If you took trace, you would end up with trace of sigma 1 A is trace of this guy 0. This gives you twice A1. Sigma 1 sigma 2 is I sigma 3 whose trace is 0, and so on. So it is clear that you end up with A1 half trace A sigma 1 and so on. So formally that is the inversion, similarly for A2, A3, etc. So it is evident immediately that any 2 by 2 matrix can be uniquely expanded in terms of the sigma matrices. The great advantage of this expansion is that these matrices, the unit matrix and the sigma matrices, are all Hermitian matrices, whereas the natural basis is not Hermitian. When I write a normal 2 by 2 matrix, the natural basis for a 2 by 2 matrix this is shorthand for A etc. This basis is not Hermitian. This is not a Hermitian matrix. This poses a lot of difficulty. On the other hand, the sigma matrices are Hermitian, that is a great advantage. So that is the reason one uses, one of the reasons why one uses the sigma matrices. The other thing is that exponentiation becomes very simple, because e to the power I a dot sigma, where a is an ordinary vector a1, a2, a3. This has a very simple expansion in terms of the cosine and sine of the modulus of a. This is, it is easy to verify, because you expand this and then the first term, for example, the identity plus I times a1 sigma 1 plus a2 sigma 2 plus a3 sigma 3, and then the same thing squared. But in the squaring of a dot sigma, you will get terms of the form a1 a2 times sigma 1 sigma 2 plus sigma 2 sigma 1, and that will vanish because it anti-commutes. So only the terms which are the squares of the sigma matrices would contribute when you exponentiate, and the result is this too is a 2 by 2 matrix, this is also a 2 by 2 matrix, so it should also be expandable in terms of the unit matrix and the sigma matrices, and the expansion is cos a times the unit matrix plus I a dot sigma over a sine a, where a stands for the square root of a1 squared plus a2 squared plus a3 squared. Very, very useful representation. In fact, you can now see what a 2 by 2 what a rotation is going to do, and we will see that very shortly. When you rotate the coordinate system, you could ask what happens to any operator in this space, and it will be rotation, the representative of the rotation operator times the operator times the inverse of the rotation operator, and this will be easily calculable using this identity here. Now what I have given here in this problem set is a whole lot of vector identities using sigma matrices. Among them, let me write down a couple of them because they are useful for what we are going to do later. You have a dot sigma times b dot sigma, and this turns out to be a dot b times the unit matrix plus I times a cross b dot sigma. This is a scalar quantity and that is a scalar quantity, but each of them is matrix valued, they are all matrices, and that is the unit matrix plus something which depends on the sigma matrices, the coefficient is a cross b. Okay. So the commutator of a dot sigma with b dot sigma is twice I times a cross b dot sigma, because it would just be the inverted thing, and b cross a would be minus a cross b, and that cancels the minus sign of the commutator and you would get twice this flow. Then the other one that you need is sigma with a dot sigma, this is equal to 2I a cross sigma. And similarly sigma, this is one more, sigma cross any unit matrix, unit vector, sigma dot the same unit vector is sigma minus I sigma minus I times sigma dot n, etc. All these identities are easily proved by using the commutation relations of the between the sigmas. So much for some mathematical aspects of the sigma matrices. I have already explained where the spin of a particle comes from, the fact that particles are really, their wave functions must transform in a given manner under transformations of the inhomogeneous Lorentz group, namely under rotations, velocity transformations, translations of the space-time axes. This implies that all these wave functions are labeled by a certain set of quantum numbers, among which are the rest mass of a particle and the spin of the particle, or the intrinsic angular momentum of the particle. and in that classification particles like the electron, the neutron, proton, etc., they have spin quantum number half. Particles like the photon have spin quantum number 1. There is a whole host of particles with other spins. Okay. Now spin half integer spin particles are called fermions, because when you put a collection of them together they obey Fermi statistics, Fermi-Dirac statistics, whereas integer spin particles are called bosons because a collection of them obeys Bose-Einstein statistics, and a little later we will talk about these statistics, the differences between the two. Right now I would like to point out that the way you probe the spin of an electron, a single particle like an electron, is by using a magnetic field, and the reason is as follows. We talked a little bit about this earlier, so let me continue on the same lines. The spin operator of an electron, let me put a subscript E for a moment just to tell you it is an electron that I am talking about. This is h cross over 2 sigma. So its eigenvalues, the eigenvalues of any component are guaranteed to be the eigenvalues of sigma dot n, where n is a unit vector and they are plus or minus 1 multiplied by h cross over 2. Okay. Now what we do know is that the magnetic moment, intrinsic magnetic moment operator of an electron, mu e, this is equal to a factor called the G factor of the electron multiplied by the charge of the electron divided by twice the mass of the electron. E over 2m is a standard gyromagnetic ratio if you have a classical orbiting particle of charge E and mass m. That is the one proportionality constant between its magnetic moment due to the current loop that it forms when it rotates, revolves in an orbit, and the angular momentum, orbital angular momentum. That relation is generalized to G E over 2 me times the spin operator of the electron. So this, if I put this in, is equal to G, the charge of the electron, twice the mass of the electron, there is an h cross over 2 and then sigma. Therefore the eigenvalues of any component of the magnetic dipole moment, intrinsic magnetic dipole moment of the electron, are given by plus or minus this quantity, because this quantity, any component of it, has eigenvalues plus or minus 1. Okay. But the G factor of the electron itself turns out to be 2 from relativistic quantum mechanics. So this is input information. There is no way of deriving this G factor in classical physics, it is not a classical concept, or even in non-relativistic quantum mechanics. It has to come from relativistic quantum mechanics, which predicts that the G is equal to 2. Actually the G, if you measure it exactly, is not 2, it is a little different from 2 with a small correction, and this correction is known to a very large number of places and has been verified. The correction comes due to what are called radiative corrections due to quantum field theory. We are not concerned with that right now, we will simply put in the fact that G is equal to 2, put in this experimental fact, and therefore this becomes equal to minus charge modulus of the charge in the electron H cross over 2 E times sigma on putting in this 2. And this is equal to minus the Bohr magneton times sigma. Okay. So if you are in an SZ equal to plus half state, which corresponds to saying sigma 3 equal to 1, then the magnetic moment in the Z direction has a value minus the Bohr magneton, otherwise it has a value plus the Bohr magneton in the other state. Okay. and this difference in the sign between the magnetic moment and the spin comes about obviously because the charge of the electron is negative. Okay. So this is really all one needs to know. Okay. The moment you put this electron in a magnetic field, if it is a uniform magnetic field, then it experiences a torque. This dipole moment experiences a torque, and the magnetic Hamiltonian, magnetic part of the Hamiltonian is equal to minus mu E dot B. That is the potential energy. Okay. And if I put this in, this is equal to Bohr magneton times sigma dot B. The minus sign goes away, and this is your magnetic Hamiltonian. Okay. What are the eigenvalues of this Hamiltonian? What would be the eigenvalues of this Hamiltonian? Well, sigma dot B is a component of sigma in some direction multiplied by the magnitude of B, right. So it is clear, could take this to be the unit vector, when you divide it by its magnitude you would get the unit vector, and that portion has eigenvalues plus or minus 1. So it is clear that the eigenvalues are equal to plus or minus B times mu over magneton, where this is the magnitude of the magnetic field. Is this clear? Since we know that sigma dot any unit vector has eigenvalues plus or minus 1, that is it. Okay. Plus B mu B when sigma z has got, if B is in the z, the spin points along the direction of B, and minus if it points in the opposite direction. Okay. So at this level it is completely trivial. Now what we would like to do is the following. Given this, we would like to do the following. We would like to ask, here is my Hamiltonian, and I am going to ask, I start in an arbitrary state of the electron, and remember that this state here can be represented by 1 0, and this state is conveniently represented by 0 1. I choose the z axis as my axis of quantization for the moment. Then the complete set of states, spin states of the electron, they can is comprised of just two states, two orthonormal states, which is this and this, and they are each normalized. So and the other way about too. The complex conjugate of this is just going to come bring this here and that there, and that is also 0. Okay. So now I ask, suppose I start in an arbitrary state, spin state of the electron, and here is my arbitrary state, chi equal to A B. That is an arbitrary state of the electron. I would like to start with a normalized state always. So I am going to impose A and B are two complex numbers which satisfy mod A squared plus mod B squared is 1. Okay. In this state, what is the probability that the Sz component of the electron has eigenvalue plus half h cross? How would you compute that? Well, it is clear that the probability we ask for, P up, we want the probability that the spin is up. This is equal to the modulus squared of this probability amplitude by definition. This is the probability amplitude that when it is in the state chi it is in this state up, and the mod squared of it is the probability itself. So what is this equal to? Mod A squared, and similarly P down equal to down chi on P squared. Okay. Right. So that is my initial state. Now I switch on a magnetic field in some arbitrary direction. What would happen to this state? Would these probabilities be the same? First let us ask a very simple question. What if I switch on a field in the z direction itself? Will this state change? Will chi of t change? So here is the Hamiltonian, in all cases here is the Hamiltonian. So what would happen to that state? Let us say I start with, that is my 0 state, I start with that at t equal to 0, what would happen to this state? So I put B, this implies the Hamiltonian is B mu B sigma 3. That is the Hamiltonian. So I ask chi of t equal to e to the minus I by h cross h t chi of 0. This is equal to e to the minus I over h cross, the Hamiltonian is B mu Bohr magneton, which is modulus E h cross over 2 me. I just expand what this mu B is, and then sigma 3, there is a T as well acting on AB. So what does this give us? There is an h cross which cancels out, and what does this give us? I need to use that expansion that I wrote down in terms of cosine and sine and so on, right? I had this, let's write that out just for convenience. E to the I A dot sigma is equal to cos A times the unit operator plus I A dot sigma over A sine A, and e to the minus I that is just a minus here, the cosine does not change sign. So let us use that. And what is A in this problem? A dot sigma, A is along the z direction, there is just one component here. So what does that give you? A in this problem is equal to modulus E B over 2 me time multiplied by time multiplied by this. Agree? So what would happen here? It would be cosine mod E B. Oh, incidentally, what's this guy equal to? What's EB over 2m? It's a cyclotron frequency, right? Is it the cyclotron frequency or twice the cyclotron frequency? Or half the cyclotron frequency? half the cyclotron frequency. Because remember there is a difference between a classical orbiting particle and the spinning electron, because this has a g factor equal to 2. So this constantly there is going to be change of factor of 2 everywhere. So you have to be careful. I have written it down carefully in the notes. So this is equal to cosine omega ct over 2 times the unit operator minus I a dot sigma, and the a part simply cancels out, and then you get sigma 3 sine omega ct over 2 acting on AB. Now it is trivial to find out. So what does this give you? It is cosine of this minus I, and the top element of the 1 element of sigma 3 is just 1 minus I sine. So it is e to the minus 2 on A, and the other one, the bottom element, occurs with a minus sign, so that becomes a plus here, e to the Do the probabilities change? They can't, because your Hamiltonian is also diagonal in sigma 3, right. So the probabilities do not change, there is no flip at all. Mod A squared and mod B squared are exactly the same at mod A of t whole squared and mod B of t whole squared. If I had a field which had any component other than the 3 component, then of course there would be a off diagonal elements here. For example, if there is a portion of sigma 1 and a sigma 2, there would be off diagonal elements here, and they would mix up things between these two, and then you would get oscillations, and then the probabilities would indeed change. This means that the spin up and spin down, the total probability always remains 1, but there are transitions between the 2 spin states caused by a transverse field. What we asked for here is somewhat more interesting than that, and that is the following. The idea was to find out how this magnetic dipole behaves in a magnetic field, what kind of precession or precessional motion it undergoes. And let me point this out carefully, because consider a classical particle of radius r orbiting in a radius r. The charge of this particle, let us say, is E, and the mass of the particle is m. Then what is the relation between the magnetic moment and the orbital angular momentum in this case? The orbital angular momentum is mr squared times the angular velocity of this particle, which is 2 pi over the time period in the direction of r cross p. So let us say some unit vector n in this fashion. The magnetic moment, the magnetic dipole moment of this particle by Ampere's law is the area of the current loop multiplied by the current. The area of the current loop is pi r squared, and the current is E over t, and it is also in this direction n. So this gives you a relation between L and mu. The gyromagnetic ratio, not surprisingly, is E over 2m. There is a 2m factor here and there is an E here, so E over 2m is the gyromagnetic ratio. Mod mu equal to E over 2m mod L. What is dl over dt? What is the rate of change of angular momentum? It is equal to the torque. It is equal to mu cross b. What is the frequency of precession? What is the Larmor frequency of precession? What you have to do is to convert this L. Okay. So if you call this constant gamma or something like that, so you write mu equal to gamma L, this fashion, then L is mu by gamma, so this would imply d over dt mu equal to gamma times mu cross b, implies frequency of precession modulus gamma b. That is trivial to see from this equation. Once you get an equation like this, you know it is precessional motion, and the frequency of motion is just the magnitude of gamma times the magnitude of b. So in the classical case, this would become modulus Eb over 2. What happens if you put a quantum mechanical particle in there? Then for the spinning particle, ds over dt, the spin operator ds E over dt, this is equal to, we got to compute what this guy is. We can't just write it down as torque because that is a classical equation of motion. I have to calculate what this quantity is. How do I compute it? How do I find it? What equation of motion do I write? This is a Heisenberg equation of motion. I have no choice. So I have IH cross ds E over dt on this side is equal to the commutator of the spin operator with the Hamiltonian. And what is this equal to? This is equal to h cross over 2. So let us take out that h cross over 2, h cross over 2 sigma, that is SE, with the Hamiltonian. But for the Hamiltonian we had a very simple expression in an arbitrary magnetic field. And what was that? There is a Bohr magneton multiplied by sigma dot b. Right? This is what we discovered. This is equal to, so this says d SE over dt is equal to minus I, because I am going to bring this I to this side, so minus I, the h cross cancels, the factor 2 remains, mu b remains, and then the commutator of sigma with sigma dot b, but we have a convenient expression for it. Sigma with a dot sigma is 2I a cross sigma. These are vectors, remember, they stand for all three components together and they do not commute with each other. That is the reason you get non-zero answers here. But you could write this as a dot sigma or sigma dot a, that does not matter because a is an ordinary vector just as the magnetic field B is an ordinary vector. So you got a 2I B cross sigma, this is multiplied by 2I B cross sigma. Which is equal to, the 2's cancel, I want to be very careful now, this is equal to minus mu b, b cross sigma, plus mu b, b cross sigma, that is equal to minus mu b sigma cross b. So this was my classical equation, and now I would like to write the quantum equation, and the quantum equation says ds E over dt is equal to minus mu b. So this is minus modulus E h cross over 2 me times sigma cross b, which is equal to E over me this side h cross over 2 sigma is the spin operator. So spin operator cross b. Okay. Therefore again you have precessional motion, but what is the frequency of precession? It is E over m and not E over 2m, and the reason for this difference was because of the g factor of the electron. So the precessional motion still appears, it is exactly the same as before. In fact, what was the magnetic what was mu e? Mu e was equal to, in terms of the spin operator, what was this equal to? G is 2, so it was, yes, it was G E over 2m, 2m e, yes, into h cross over 2 sigma, right, into the spin times the spin operator here, right. So this was exactly equal to E over me S E. So in fact you could write this as mu E cross B. So the point is the following: the classical equation of motion says rate of change of angular momentum is equal to the torque. The torque on a dipole of magnetic moment mu is mu cross B. So it says dl over dt is mu cross B. Quantum mechanically, the exact equation of motion for the spin operator, which is an angular momentum operator, is rate of change of the angular momentum operator is again equal to mu cross B. The difference, however, is, so therefore the equation of motion does not change at all. This is another example of Ehrenfest's theorem, because if I took expectation values on both sides, then it says this is equal to that, because those are the operators. And Ehrenfest's theorem says that quantum mechanical expectation values obey classical equations of motion for these simple Hamiltonians, for such classes of Hamiltonians, and that is exactly what has happened. It is exactly the same equation. But when you want to actually compute what the precession frequency is, you have to convert this mu into an L, or you have to convert this L into a mu, because that is how you get the precession of mu. So you have to convert this S into a mu. The factor that converts is in fact the gyromagnetic ratio, appropriate ratio, and that is E over m here. So the frequency of precession is equal to modulus E over m, whereas the frequency of precession here equal to modulus E over twice m. But yeah, I am sorry, EB, both sides, quite right, yeah. If you have, the way classically you have a magnetic dipole moment is by imagining there is a current, motion of a current in the form of a loop, a current loop. So I said let us take the simplest instance where you have a particle moving in a circular orbit of radius r and so on, and found that in the classical case the gyromagnetic ratio is charge divided by twice the mass. Okay. Here for the internal motion, for the spin degree of freedom, the relation between the magnetic moment and the angular momentum, intrinsic angular momentum, has an extra factor g. which happens to be 2 for the electron, which implies that even though the expectation value of this angular momentum undergoes precessional motion exactly as the classical counterpart would, the frequency of precession is Eb over m here, but it is Eb over 2m here. That is because there was that extra g factor sitting there. Okay. But otherwise the equations of motion are exactly the same in both cases. Rate of change of angular momentum is magnetic moment dipole moment cross the magnetic field, the torque. It is exactly the same equation, except in classical mechanics you write that down from the rules of classical electromagnetism, but in quantum mechanics you have to compute it given the Hamiltonian. You actually have to calculate this commutator here, and we have discovered you get exactly the same equation of motion. Now what I would like to do is to ask, suppose I have a general Ket vector of this kind, could I interpret this Ket vector? We know that if it were 1 0 I would say that corresponds to an eigenstate of Sz. If it was 0 1 eigenstate of Sz with the opposite eigenvalue. What happens if it is some A B? Could I interpret it as the eigenstate corresponding to plus half h cross of some spin pointing in some arbitrary direction? This is the question I would like to ask. Is the question clear? Suppose I chose my axis of quantization along some arbitrary direction, then could I interpret this AB, this Ket vector, as the eigenstate corresponding to spin up in that new direction? So let us see if that works out. That will be very useful for what we are going to do next. So let us take some arbitrary unit vector n in space with respect to my fixed coordinate system, some arbitrary unit vector n specified by polar angles theta and phi. What are the components of this n? It is a unit vector, polar angles are theta and phi, the magnitude is 1. So what is it in spherical polar coordinates? Yeah, it is equal to sine theta, cos phi, sine theta, sine phi and cos theta, such that mod n squared is 1, n dot n is 1. Okay. Now we would like to ask, let me make the question precise. What is this, what is the upstate for this? I would like to know what is the upstate for this guy. So let me denote it by this guy here. Let me denote this equal to upstate of S dot n or sigma dot n. And the opposite arrow would be the downstate of this guy. So what should I do? I would like to find that upstate. So I would say okay, so I expand this upstate. Any arbitrary state can be expanded in eigenstates of Sz, which was my original axis of quantization. So let me simply expand, let me simply write upstate here is equal to some A times 1 0 plus B times 0 1. Let this be true. I know that sigma dot n on this state must be equal to 1 plus 1 times the same state. I require it to be an eigenstate of plus half h cross. So when I multiply the sigma by h cross over 2, then I am going to get s dot n, and the eigenvalue is plus half h cross. So that is why I put a plus 1 there here. So we require this, and we have to solve this eigenvalue equation. That is all we have to do. And what does this give you? Sigma dot n is sigma 1 times this guy. So it is clear that sigma 1 is off diagonal completely, sigma 2 is fully off diagonal, sigma 3 has diagonal terms, and we want sigma 3 times n3, which is cos theta here. So this will give you cos theta minus cos theta on this side, and then sigma 1 is 0 1 1 0, so it is going to give you sin theta cos phi. Let us write it out with enough space, sin theta cos phi, and then sin theta cos phi acting on a b is equal to ab. That is my eigenvalue equation. This is just, this operator here is just ab, so this ket vector is just ab. Then I have sigma 2, which is multiplied by this coefficient, but sigma 2 is a minus I, so this is equal to sin theta cos phi minus I sin theta sin phi. That was this guy here, and then plus I sin theta sin phi, and then minus cos theta. That is my eigenvalue equation. My job is to find a and b and normalize it to unity, and then I am guaranteed to get this ket vector ab is the eigenstate of sigma dot n with eigenvalue plus half plus 1. So this gives you cos theta minus I sin theta, sin theta comes out common, cos phi minus I sin phi is e to the I phi, e to the minus I phi, and this fellow here is e to the I phi sin theta sin theta. Those are the eigenvalue equations. So what does it give you? A cos theta plus b sin theta e to the minus I phi equal to a, and similarly a e to the I phi sin theta minus b cos theta equal to b. Either of them would do, because this is something where you are going to normalize a and b such that mod a squared plus mod b squared is 1. So it says b sin theta is a into 1 minus cos theta. You do not need this guy, that fixes your b, and then I normalize it to unity. So b, this can be written as 2b sin theta over 2 cos theta over 2 is 1 minus cos theta, which is 2a sin squared theta over 2. So the 2 goes away on both sides, a sin theta over 2 goes away, and it tells you b equal to a tan theta over 2 a to the I phi. Okay. So I have in fact written the answer down. So let me write the answer down after you normalize it. You get this guy is equal to cos theta over 2 and then e to the minus I phi sin theta over 2. Okay. That is the normalized state. Mod a squared plus mod b squared is 1 in this case. It is worth remembering this expression because you can then write down things very fast. By the way, the overall phase factor is irrelevant because you can always multiply this by some e to the I alpha and it will not change any probabilities, it will not change any physics at all. So you could, if you like, make this look a little more symmetric by multiplying by e to the I phi over 2, in which case you get e to the I phi over 2 cos theta e to the minus I phi over 2 sin theta over 2, looks a little more symmetric. But this expression is worth remembering because it keeps appearing over and over again. So you agree that if you give me any arbitrary ket a b such that mod a squared plus mod b squared is 1, I could interpret that ket as the eigenstate of S dot n with an appropriate n. The angle n, the polar angles of n are given by the a's and b's in this fashion. The relative phase difference between a and b is the azimuthal angle. And a is like cos theta over 2, b is like sin theta over 2. So the ratio of a to b in fact gives you the cotangent of theta over 2, or b to a, mod b over mod a gives you tan theta over 2. So that is the way to interpret an arbitrary state a b. Now you can quickly check that all the usual results will come out. For example, if theta is 0, that means the axis of quantization is z axis itself, I should get 1 0, and indeed I do. What happens if theta is pi? You get 0 1 apart from a phase factor which is irrelevant because along the z axis the phi angle is undefined anyway. So that works. What about this? What about this eigenstate? What is this equal to? Sx equal to h cross over 2 plus h cross over 2. What kind of state corresponds to plus half h cross by 2 as the eigenvalue for Sx? All you have to do is to substitute values of theta and phi into it. What about the x axis? What does that correspond to? What value of theta does it correspond to? Pi over 2, because pi is the north direction, pi over 2 is the equatorial plane, right. So this is pi over 2, phi equal to 0. So what does this become in the z basis? In this basis, what does it look like? This is cos pi over 4, which is 1 over root 2, this is gone and that is also 1 over root 2. So it is clear this is just 1 over root 2 1 1, and the same thing is minus. What would happen? What would that correspond to in terms of phi? Phi goes to pi, from 0 it goes to pi, it is the negative x axis, so that becomes plus or minus 1. What about this one? Sy equal to plus or minus h cross over 2. What would these correspond to? Now we want to know the coordinates of the y axis, the positive y axis. Again theta is equal to pi over 2, but phi is either pi over 2 or 3 pi over 2 in the other direction. So this is equal to cos theta over 2, that is equal to 1 over root 2, once again comes out always, and then this guy is a 1, and when phi is equal to pi over 2, it is e to the minus I pi over 2, which is minus I, and e to the minus 3 I pi over 2 is e to the plus I pi over 2, which is plus I. So this is 1 minus or plus I. So if you see such states, you instantly recognize that these correspond to eigenstates of the x and y coordinates, but a general eigenstate looks like that out there. Now you are in a position, I am going to stop here and then we will resume this, to answer this question which says, consider an arbitrary initial state chi equal to a b, and then suppose you measure not S z, in which case the probability of plus half h cross would have been mod a squared and the other one is mod b squared, but you measure Sx, and the question is what is the probability that you obtain the value plus half h cross and minus half h cross respectively. What would you do? What would you do? You change basis. The obvious thing to do is to change basis. So you start with AB and write it as a linear combination of these two states, and then take probability. They are also orthonormal, every one of them has been made orthonormal as a basis, and then identify the coefficients. So in that case the answer would turn out to be mod a plus b whole squared over 2 and mod a minus b whole squared over 2. Similarly, if you measured Sy, the answer would be a plus ib mod squared and a minus ib mod squared, and half of these quantities give you the probabilities. So I hope it is clear what is happening. You started with an axis of quantization by convention, the z axis, and I took an arbitrary ket vector and identified it with the eigenstate of S dot n, a particular n, but I use that backwards to write down what the eigenstates are for any axis of quantization directly. And if you want to know what happens if I take an arbitrary initial state and measure in any other component, any arbitrary component, what are the probabilities of getting plus or minus half h cross, because those are the only two answers possible. The answer is take this ket vector and expand in that basis, so it is just change of basis, and take the mod squared of the coefficients, that is it. Okay, so let me stop here and then we will resume after a little while.